Yeah, cool. Thank you for the introduction. Yeah, so this is a bit of a departure from some of the other talks. But Landau levels, I guess, are the original flat band, so I guess that's fine. But I think the lithographic techniques that I'll talk about may have particular relevance for doing mesoscopics for a wide array of van der Waals materials, so hopefully this will be an interesting talk for you guys. So the first thing I'm going to do is just do a very brief introduction to quantum Hall physics and graphene van der Waals heterostructures, talk about our fabrication techniques and 2 experiments that we've done in quantum point contacts and in Fabry-Perot interferometers, as well as some future outlook. So a flash introduction to the fractional quantum Hall effect. Basically, you have a state of matter that is characterized by a 1D chiral edge mode that is dissipationless, giving you a longitudinal resistance that vanishes in a fractionally quantized Hall conductance. So basically, the edge is conducting, and it has these fractional quasi-particles, in particular for like nu equals 1/3 filling of a Landau level. You get E/3s, and then in the insulating bulk, you get strongly localized fractional charges as well. The other thing that you can get in this system is a non-Fermi liquid at the edge. It's pretty easy to understand why. Basically, if you have these E/3 modes that are propagating along your dissipationless chiral edge mode, if you try to tunnel an electron into it, there's just no available states for that electron. So this leads to a vanishing density of states at the Fermi level that is actually predicted to decay with a very particular power law that is dependent on the wave function and the bulk topology of the system, and should give you a power law dependence of the tunneling conductance that scales both quadratically for the nu equals 1/3 state in temperature and in voltage. And then you also have this very interesting fractional exchange statistics of anions, where you get, if you take 2 E/3s, for example, and you swap them, in 2 dimensions, you're allowed to actually have a non-trivial phase when you swap them in the many-body wave function. Okay, so very basic stuff that you're hopefully all familiar with. But we're interested in probing these properties of this system and fractional charge, statistics, and non-Fermi liquid behavior. And I'll talk about experiments that touched on all 3 of these. And we need a good 2D system, so graphene is our material of choice. Shock and surprise. And we need to be able to manipulate the edge modes and quasi-particles in a way that doesn't introduce uncontrolled disorders on the length scales relevant for mesoscopics and on the energy scales relevant to fractional quantum Hall gaps. Okay, so how do we make these things? We take exfoliated flakes, and we, with much pain and suffering, stack them 1 layer at a time and assemble them into these heterostructures where we have essentially a monolayer graphene that is encapsulated in boron nitride, and then also encapsulated with graphite that we use as a gate layer. The mantra of this type of fabrication is really to isolate the graphene from the world as much as possible, and in order to make essentially an atomically clean and atomically uniform interface. So is this worthwhile? And in fact, it definitely is. So very routinely in our lab, if we measure just magnetotransport, both in high field, as a function of gate voltage or electron density in the monolayer, we find a cornucopia of fractions, vanishing longitudinal resistance, quantized Hall conductance. It's really great. You can have all these that are accessible via field effect gating, so you're not limited to a particular magnetic field. You can tune to whatever field you want and get whatever fractional quantum Hall state that you desire. More so, the system is extremely nice because the energy gaps are exceptionally large. So for example, this is a chemical potential measurement in the first 2 whole Landau levels of monolayer graphene. So every time you see a jump here, that's just basically measuring the height of the gap. And you can see that the fractional quantum Hall states are on the order of millielectron volts. So for the 1/3, you've got a 70 Kelvin thermodynamic gap that corresponds to a 23.3 Kelvin activation gap. So these extremely large gap devices, which is very nice for just doing very clean fractional quantum Hall physics. And the proximity of the 2-deg to gates, because the HBN dielectrics tend to be between 10 and 40 nanometers, gives you essentially very sharp confinement potentials and improved screening without reducing the gap sizes. So that helps with making mesoscopics by reducing charging energies. So that could be good for making interferometers and for quantum point contacts. Okay, so that's sort of the why graphene. Now let me talk about our lithography technique that we've used to make these very clean mesoscopics. So like I said, the whole mantra of 2D materials has been really to isolate graphene from the world as much as possible, right? But if you want to do anything kind of interesting with it, you have to remove the top graphite layer, part of the bottom graphite layer in some way. So for example, if I wanted to trap an electron, I'd have to take a chunk out of this graphite somewhere. And that sort of gets rid of this whole beautiful fractional quantum Hall, these very clean systems, because you've now just removed the thing that actually made the system clean in the first place. So this is going to be seen just to sort of reiterate this point, which is that if you try to remove it using standard like nanolithography techniques, you're going to etch away that, you're going to etch away the graphite, and you're going to leave some charge disorder potentially in a critical region. Sort of if you make a split gate device like this, if you try to define a gate-defined edge, you're going to have disorder basically at the critical junction where your edge state is going to live. So that's bad. So how do we do this? Our solution to this technique is fundamentally based on pre-patterning the graphite before we integrate it into the heterostructure. So we use local anodic oxidation. Basically, we take an AFM tip and we bring it close to the graphite. In a humid environment, a water meniscus will form between the graphite and the conducting AFM tip. And that just happens via capillary action. And then you apply an AC voltage, and that electrochemically oxidizes the graphene. You can do nanoscale subtractive lithography, sort of on the order of 50 nanometers, just by chemically ablating away the graphite. The amazing thing is that, okay, fine, so you have this electrochemical reaction that takes carbon to carbon dioxide, but there's a lot of other things that can oxidize with carbon. And you get a lot of other like graphene oxide residues. So what tends to happen is that those actually, by some miracle of science, preferentially stick to the SiO2 when you then pick up that microtextured flake with an HBN crystal. So let me not just like pretend, let me just show you. So these are basically AFM topographs taken after AFM cutting a graphite, basically before transfer and then after transfer. So the idea is, you can make a whole bunch of different structures with this. It's a very versatile technique. You can get down to sort of 50 nanometer scale cuts. You can see sort of in the most stark version of this like whole array in graphite. You can see a lot of these very sharp features in the topographs indicating essentially oxidized residue. And then when you pick it up with HBN and rescan it, it's all gone. So you get this really beautiful self-cleaning ability with this type of material where you start with actually a cutting technique that leaves some kind of disorder, but then when you actually integrate it into the heterostructure, you end up with something clean. Okay, so now I'm going to just move on to the experiments now, sort of get over with the sort of boring fabrication stuff. So we use this technique, this AFM anodic oxidation, to cut, for example, for our first experiment, we're going to do a quantum point contact, so we cut an X-shaped geometry. And this gives us essentially 4 distinctly controllable gate regions. So we have our AFM cut top gate, monolayer graphene, and then a graphite bottom gate. And what we do is we can use the north and south regions to deplete the electron density to form the quantum point contact. Then we have individual control over the east and west regions. So on one side, we tune to the nu equals 1/3 state. And on the right-hand side, we tune into the nu equals 1 state. So this is forming a quantum point heterojunction between these two states of matter. And the experiments that we're going to do, very simple electrical transport. We're just going to do this thing called diagonal conductance, just the Hall conductance across the device. So essentially what we do is we measure the current on the output, source voltage on the other side, and measure the cross-device voltage. And the expectation should basically be that as you have some finite transmission of electrons going from the 1/3 side to the 1 side, you should get basically the transmission coefficient times e²/3. That's sort of the types of things that you should be studying. So we're sort of interested in understanding what the transmission coefficient is. So what is the sort of plot that we tend to look at? Well, the thing that we do is we look at conductance versus voltage bias and the north and south gates. So the north and south gates electrostatically tune the energy barrier of the quantum point contact. So as we decrease as we move more positive on the north and south side, that's going to enhance, that's going to reduce the barrier, so it's going to make it more transmissive. And as we deplete the north and south gates, it's going to make the QPC intrinsically more reflective. And you can see here that we go from basically having no conductance to having finite conductance. So I'm going to, sorry. Oh, this is not clicking the wrong button. Anyway, we're going to focus on this point over here to start. So the thing that you expect to happen in this system, right, is basically just a model. So a lot of math. I'm not going to go over it too much, so don't freak out. It's cardinal sin for an experimentalist, I know. But the basic idea is that you've got electrons going from the left-hand side to the right-hand side. And this model just encapsulates that one single operator, electron going from the left-hand side to the right-hand side with some tunneling rate gamma at a single point. The beautiful thing about this model is that gamma is an irrelevant operator. Its scaling dimension is -1. So as you go to lower and lower voltage biases and lower temperatures, the expectation is that the perturbation theory should become more and more valid. So you can do the perturbation expansion, and the expectation is that in the low energy limit, you get a conductance that scales as T² and V². This is the Cairo-Luttinger liquid behavior that I was talking about in the beginning. And in particular, you have one additional energy scale, which is the raw energy scale of the QPC. Okay, so how does this stack up when we do the measurement? If we do the measurement and we look at the voltage, we look at the bias dependence at this point, we see a very beautiful, like G equals 2, quantized Chiral-Luttinger liquid value. So this is sort of exactly what you expect, V squared scaling conductance. And the thing that you can do is you can actually look at the curvature of this parabola. So you can look at the curve, basically at our lowest temperatures. You can take this formula and you can expand it out, and you can see that the 2 pi t squared will cancel on both the top and the bottom, such that you can extract the T naught just from the lowest temperature bias dependence, so no temperature there. So this curvature tells us T naught, which is in this case it was 9 Kelvin. And then if you take that prediction and then you just say what is the zero bias temperature dependence and take that theoretical data and plot it to our temperature dependence at zero bias, you can see that they actually agree very well. So this was not fit at the we didn't fit the temperature, we just took the information from the lowest temperature bias data and plotted that against our experimental data at zero, conductance versus temperature at zero DC bias. So that does agree quite well. We can take this one step further. We can adjust our north and south voltage to change the QPC set point a little bit to change T naught. And we can actually do this really beautiful scaling collapse. So we can take the conductance versus voltage bias for an array of different temperatures. And the expectation is if you take this conductance, and then for every single one of these traces, divide it by 2 pi t over T naught squared, where T naught is just extracted from one single trace. So we extract that from the lowest temperature trace in the bias dependence. So we don't extract that from temperature. You take that, and then you take each one of those successive curves and divide it by 2 pi t over T naught squared, and plot it as a function of EV over 2 pi kBt. You should get the same curve every single time. And in fact, in the low energy limit, you do. So we see that the curves, this dashed white line is basically just this formula over here, and we see that these curves collapse onto each other in the low energy limit and deviate in the high energy limit where you expect it to. Yeah. Yeah. So I changed the QPC set point. So I moved to this point. But we can do it here too. That's in our paper. Okay, so remarkably, this fitting to the Luttinger liquid behavior is actually not the most interesting thing that happens in this experiment. So one thing you may notice is that there is a consistent saturation to 1/2 E squared over H as the transmission coefficient is enhanced. So as we actually open the QPC more, we don't see E squared over 3H, we see E squared over 2H. So we see this excess conductance. Now that's quite strange, as I said, because you have a 1/3 edge mode talking to a nu equals 1. And the expectation is that if you were to try to transmit all of your electrons from the 1/3 side, really you should just max out at 1/3 E squared over H. But we actually get more than that. And there is actually a very simple explanation for this, which is that the prediction at basically high tunneling rates, there is a dominant scattering process, which is analogous to Andreev reflection in a superconductor. So the expectation here is that you've got 2 E over 3 charges that come into the junction, and to transfer an electron, you retroreflect a quasi-hole. And you can see why this would give you an enhanced conductance, because this is effectively like having a 3/2 transmission coefficient. You've got 2 E over 3 charges coming in, and then you have basically an electron being transferred, so the ratio of those two charges is 3/2. So T equals 3/2, and you've got T times E squared over 3H, which gives you 1/2 E squared over H. But there's an extra prediction. The thing that you can do in this system that you can't do in a normal superconductor is the retroreflected quasi-hole goes downstream the chiral edge mode to a different contact. So what we can do is we can actually just measure the reflected voltage and say that every time that we have, so basically every time we have an excess conductance, if this is the scattering process that happens, you expect that the ratio of the incoming chemical potential to the reflected chemical potential should be -1/2, because you get a negative charge. And in fact, that's exactly what we see. So as we open the junction, so just as a function of north and south gates, as we enhance, every time we see an enhanced conductance above 1/3 E squared over H, we start to see a negative chemical potential develop. And when it saturates to 0.5, we see this also saturate to around -0.5. You can actually do some pretty interesting stuff with this too, which is that if you bias the junction from the other direction, you get a different process called electron splitting, where if you bias from the nu equals 1 side, 2 electrons come in, and with probability equals 1, 1 gets transferred and 1 gets reflected. And you can use this to actually make an impossible circuit element, which is a dissipation-free DC step-up transformer. So this is predicted by Shklovsky and Halprin in in the 90s. And the idea here is that you just, in order to get gain for any type of passive, any type of like non-active circuit element, you need to have some kind of current splitting, right? You need to have, if I just have conserved power, then I need to basically, if I have V2 over V1, then my I2 over, then that implies that I2 has to be less than I1, so I need to split current. And in AC, that's pretty easy to do with basically like time-changing magnetic fields gives you a displacement current, so you can do that type of current splitting. But in DC, anytime you try to do that, either with a resistor or a quantum point contact, you get dissipation. So that ends up giving you, that overall reduces your gain. So this system, though, because this splitting process happens with unit probability, you have this correlated process where 2 electrons come in and they split, you end up with the possibility to make this step-up transformer. So we did that measurement. We basically just measured the DC gain and found that it was very close to the theoretical limit. OK, how much time do I have? Sorry. 9 minutes. Great, OK. So I'm going to switch gears a little bit. So that was one experiment. Now I'm going to talk about another experiment, which is our measurements on Fabry-Perot interferometers. So as my PI would say, if you can make 1 quantum point contact, you should be able to make 2. We did that. So what is an edge state Fabry-Perot interferometer? Well, basic idea is that you've got 2 quantum point contacts in series. And the idea is that when you tune both quantum point contacts to partial transmission, you get an interference cavity where then now one edge state can actually make a complete trip around the cavity. And the phase accrued by the quasi-particles that encircle that cavity can then interfere with the incoming quasi-particles and affect your conductance. So the expectation is you get an oscillating conductance with the phase, which is mostly dominated by the Aharonov-Bohm phase. Basically, the the phase that a charged particle picks up in a magnetic field. But there's an additional contribution you can get in the fractional quantum Hall effect, which is this fractional exchange statistics. So you get, as I mentioned before, you get these localized quasi-particles in the bulk of your fractional quantum Hall system, which actually gives you, nature kind of gave us a very natural way to do this experiment, which is that now, in order to actually enact this particle exchange where I can get a phase on the many-body wave function due to like 2 anyons exchanging with each other, I get that sort of for free because if I have some number of localized anyons in the bulk of my interferometer, and then my E over 3 comes in and makes a circle, that's like doing a double exchange. And so I end up actually getting a contribution, an additional contribution to this theta beyond the Aharonov-Bohm phase, which is twice the exchange phase of the anionic quasi-particles. So this is our experiment, sort of same idea. We basically do our AFM cutting to define 2 quantum point contacts, and we have a center gate as well as a plunger gate to change the area of the interferometer. So this is what we see when we actually tune to partial transmission and look at interference in the nu equals 1/3 state. Basically, we see these generally negatively sloped lines. And that's pretty understandable because as we change the plunger gate, what we're doing is we're decreasing. So if we go in the downward direction, we're decreasing the area of the interferometer. So in order to stay at the same flux, we have to increase the magnetic field. So those negatively sloped lines are strongly indicative of having an Aharonov-Bohm dominated cavity. But the thing that's quite interesting is that these Aharonov-Bohm lines are punctuated by these very sharp phase slips. So we can ask the question, what are the value of these phase slips? Well, if we basically just subtract off the Aharonov-Bohm phase, what we find is that pretty much every single one of these sharp phase slips follows along a 2π/3 jump. So these lines each are basically 2π/3. This is in theta over 2π units. So what is going on? This is kind of slightly different than what has been previously observed in other 2-DEG systems, where sort of the addition of anyons happens over along an adiabatic trajectory and continuous with gate. So it seems like for us, what we're seeing is these very sharp phase slips. So the first thing that we checked was like, do all these phase slips happen in the same location? And the answer was no. So as we changed our magnetic field, if we do this over about 30 minutes, what we first see is we see smoothly varying Aharonov-Bohm effect. Then all of a sudden, these phase slips happen, and they continue to happen until the end of the sweep. Then we wait for a little bit, and if we sweep in the other direction, what we see is that we see smoothly varying Aharonov-Bohm phase, and then these phase slips start to happen again. So the thought here is like, are we seeing real hysteresis, or is this a feature of just a long charging timescale? Most likely a long charging timescale, as I'll show you. The idea is basically that as you change your magnetic field, you're making it more energetically favorable to add anions into the interferometer and give you a facelift, but your actual charging time for those anions is slow, so your actual chemical potential lags behind what nominally would be your equilibrium chemical potential. So we can do a kind of a nice millihertz pump probe experiment, which is we ramp the magnetic field and we wait. So we take the magnetic field. So what we're doing here is we're just, as a function of time, we're just going to sweep the magnetic field, and then that makes it favorable to load some number of anions. And what we find is that we sweep the field and we see tick, 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 tick over fairly long time scales. Each one is separated by about a few minutes. And then eventually it equilibrates and nothing happens for as long as we can measure. 5 minutes? Good, I'm almost done, so great. So this really told us that we were measuring essentially a very long time scale. So the nice thing about this, which is kind of cool, is that we can modulate the interferometer area very quickly because you can change the edge states, because they're compressible. So the time scale for changing those is fast. But adding a charge to the bulk of the interferometer is very slow. So it allows us to really actually measure the discrete change in phase for the same set of gate voltages and magnetic fields. So we can look at changes in charge configuration without changing anything else in the system. So this is basically what we do. So one thing that sort of makes this a little bit more manifest is we can start to wiggle the interferometer area back and forth. In this measurement, what we're doing is we're changing this gate instead of this gate. So that just allows us to change the area with a smaller change of gate voltage. And we can see some wiggles. Basically, what you can see is that as we what we're doing is we're just rapidly sweeping back and forth along this range of the gate voltage here. And we're slowly changing the average. So we have a rolling window of where we're doing this measurement. So we can slowly increase. And eventually, as we increase that average, it makes it more favorable to add an anion to the bulk of the interferometer. As we keep going, eventually we get a sudden facelift. So it makes it very obvious now, because again, if I keep going, I see basically, as I increase the average, I'm seeing the same range of data. So I'm seeing the same interference pattern. And then without actually changing the set point, I can actually see the change in phase. So again, I'm not changing the magnetic field. I'm not changing the overall in the overlapping regions between these data sets. I'm not changing the gate ranges. So I'm just watching charge percolate into the interferometer. And you can repeat this. And we can just measure the phase each time. Oops, sorry. And then we can just do this, and we can actually plot the phase for each one. And what this allows us to do is just look at these 3 distinct phase classes. So again, in the same range of center gate, we can see all 3 phase classes associated with adding n-1, n, and n+1 anions into the interferometer without changing the magnetic field or the gate voltage range. OK, how much time do I have left? OK, I'll just quickly go through this. This is sort of our control experiment version of this. So this long charging time scale is actually a general feature of quantum Hall states in this system. So we did an experiment in nu equals 1. So what we found was that in nu equals 1, you can see essentially small phase. You see mostly Aronoff-Bohm-dominated interference with very small magnitude facelifts that don't seem to be sort of instantaneous and irreversible. So basically, what we do is we look at sort of the edge of the plateau where things are more compressible. And what we find is that you get these as you add charge to the interferometer. The expectation is that if you have a little bit of coupling between the bulk and the edge of your system, as you add a charge, you expect some breathing of that interferometer area, and it'll change your phase. So we can actually measure facelifts in the integer quantum Hall regime without any effect from the anion phase. So the hope here is that if you want to have low bulk edge coupling, such that you can actually demonstrate that in the integer regime you have the same effects, but much smaller than what you see in the fractional quantum Hall regime, where we see mostly 2 pi over 3. So the interesting thing that we can do, is that as we increase towards the center of the plateau, the quality of these facelifts actually change. So they went from basically sort of continuous with gate voltage to then sort of in this glitchy regime, which actually has this like 2-state quantum switching noise. Basically, now we've changed the time scale from essentially continuous, so sort of faster than our measurement time of 10 milliseconds on our lock-in, to now sort of on the order of seconds. And as we keep increasing the gate voltage, what we find is that we go back to the same regime we were in the fractional quantum Hall regime, where now we have these irreversible, like sharp phase flips. And if we just plot the magnitude of all of those, they're generally quite small. So what we now know is that in the integer quantum Hall part of this region of this system, the bulk edge coupling is small. And so when we do this in the fractional quantum Hall regime, we do know that most of the contribution is indeed coming from the anion phase and not from bulk edge coupling. So yeah, this is basically a localization transition, so just taken all together as you change sort of the location of the plateau. As you have lots of density of states, you can sort of charge that continuously. And then as you change, as you move towards the plateau center, these states get further and few between, and then you end up with very strongly pinned localized disorder, giving you this long charging time. And that's it. So, what's next thing? Even denominators, obviously, is the thing that we're trying to go for. The energy gap in bilayer graphene is equivalently large for the purported Pfaffian states. So that's sort of considerably larger than 5/2. We're seeing sort of stuff on the order of 10 Kelvin thermodynamic gap. So it seems promising. So check back in a couple of months, hopefully. That's it. So I'll leave this slide here. So the main takeaways and acknowledgements. My PI, Andrea Young, and the other graduate student working on this project with me, Noah Samuelson, and also our stack master generals, which I have to thank because everyone knows stacking is miserable. Right, and then theory collaborators and Wanabe Taniguchi, of course. Thanks.
Thank you so much.